Thank you very much, Professor Skopmila, for the introduction. I would like to thank organizers, Mr. Manoj Yadav and Professor Shastri for the invitation. So I'm feeling it's much nicer to be there. So let's see, let me start now. As of the work, let me just say that I don't work in this area. So there's one colleague of mine who works in representations of real E groups, and we happened to talk to each other, and we realized that the kind of representation he was always looking for, always monomial, irreducible, I mean, nilpotent groups. Things turned out to be nice for me also, and this turns out to be something common intersection point where we didn't know the answers. So that's what we started exploring. And so those are the problems I'm going to talk about. So my goal is going to start from the finite group point, and then we'll go to the infinite case, try to bring out what are exactly the problems that we face for the discrete groups. Okay, so let's just start with finite group for the motivation. Let's say G is a finite group, and by a representation, I always mean complex representations. So the question in group theory that we always want to ask is, what are all the representations of G? So when we want to ask this question, then we of course want to ask, how do we construct representations of a given group G? And then we immediately learn this method of induction and restriction. So one kind of induction, I'm going to define certain induced representations which are interesting for me. So let's say H is a subgroup of G, and chi is a character of H. So by induced representation, let me define it just this way. Set of all functions from G to C, such that f of GH inverse is equal to chi H FG for all H in H, G in G. So this gives this is a vector space, and I can define an action of any function in this way. Then we all know that this gives a representation of G, and this is what is called monomial representation of G. And I want to keep track of this pair H chi, so I'll say monomial representation of G associated with tuple H chi. So these monomial representations are nice because of the Frobenius reciprocity. So for example, if I want to decompose this representation into irreducible, I can use Frobenius reciprocity. And if these turn out to be irreducible, this is even better. Because then if I want to know whether these are constitutes of other representation, that's easy because then I can again use Frobenius reciprocity, right? So the question that I'm interested in is given irreducible representation monomial? So I start with an irreducible representation. I want to know, is it a monomial representation or not? And the next question, which is itself also interesting, is there any group such that it's all irreducible representations are monomial, and such groups are called monomial groups. So this already So these groups appeared already in Professor Dolphy's talk, where when he mentioned this famous theorem of Takeda, that if G is a monomial group, then derived length of G is less than equal to the cardinality of the set of character degrees of G. And therefore, it follows that G is solvable. So if I have any monomial group that is solvable by this theorem, and converse is not true, and it's an open problem to know the characterization of monomial groups. We still don't know what is the characterization of monomial groups. So it's still an open problem. And but still, I can still start looking at certain kind of solvable groups and start asking whether this group is a monomial group. So for example, if I take G to be a nilpotent group, finite nilpotent group, then these groups are monomial groups. I'll indicate the proof of that, but not now, later. So if G is finite nilpotent, then G is monomial. So the questions that I am interested in is, so for the finite case, given finite nilpotent group, it's always monomial. What about for the infinite cases? So instead of taking G finite, if I take G to be infinite, so I need to make sense of, now if I'm saying infinite, let me restrict myself to the class of G finitely generated nilpotent groups. Okay, and here I need to still say what do I mean by representations. So whenever we are in infinite setting, then there are various ways one can talk about representation. So the representation that I'm talking about are algebraic representations. So what do I mean by that? I just mean representation is again a homomorphism from the group G to the automorphisms of the vectors, automorphisms of a vector space, complex vector space. And for me now, a vector space can be finite dimensional as well as infinite dimensional. I mean, it's possible. For finite groups, we know that we can always reduce it to finite dimensional cases. So we always worry about finite dimensional representations. In this case, I'm allowing be finite dimensional as well as infinite dimensional. So now, given this definition of representation, irreducible representation still makes sense. So if V is a G representation, I say V is irreducible if I cannot find a non-trivial sub-representation. If I cannot find a non-trivial sub-representation of V, then I say V is irreducible representation. Now the result that, so here I need to define irreducibility this way. I cannot really write, it's not true that a representation will be direct sum of irreducibles. So that indecomposability is here in nature. So if there does not exist W such that W is G space, okay, then V is irreducible. So the question that I'm interested in asking is that given, so here's the question that I want to know, is that given irreducible representation of a let me say something about this also. Discrete finitely generated nilpotent group, then is it monomial? So I need to again say a few words about this. So if I'm talking about monomial, I need to talk about induced representation for the infinite case, right? So let me just define this. What do I mean by its generalization of what I defined there? So let me just, so by this I mean now, as earlier, I'm looking at set of functions from G to C such that so now I want two conditions to be satisfied. One is f of g h inverse is chi h f g for all h in h, g in g. And the second case that I want is that f is non-trivial only on finite number of coset representatives of h in g. This is what is the analog of compact induction for this discrete setting. I'm looking at functions which are non-trivial only on finite number of coset representatives. That's what I call as induced representation. So when I'm saying monomial, it makes sense that just means that I'm basically asking, does there exist tuple h chi such that V is isomorphic to this induced representation, right? Given irreducible, is it true? So this is, as I said, for finite case, it is true. Every irreducible representation is an induced representation. So I'm sort of asking the parallel question here. So now let me just say, let's look at a very simple example of this. And here, I also want to say that I'm looking at discrete. I'm not giving it, there's no topology on the group, right? So I'm always thinking of these as discrete, finitely generated nilpotent groups. Let's look at a simple example of, for example, abelian groups, finitely generated abelian group, okay? So now let me just start with G being Z, okay? So this is my abelian group, and I'm looking at representations of G. So if it is a finite dimensional representation, so now I need to consider both these cases separately, right? V is finite dimensional. I look at these two cases separately. So if V is finite dimensional, then it is easy to see that I can always find a one-dimensional subspace here, eigenvector, because I can upper triangularize it's basically upper triangularize one matrix, because representation will be given by generator of G, right? And for the infinite dimensional cases, it's not true that I will be able to find one-dimensional eigenvector, but I can always find subspaces that are going to be G invariant, right? So because, for example, if V is, so here I can basically look at V can be something, a space of just G to the IV, where G is the generator of this. Then I can look at W such that W is the linear combinations, finite linear combination of elements of V. With coefficient sum 0. So these kind of properties are basically preserved. So these are going to be proper subspaces, and these are going to be G invariant. So an infinite dimensional representation cannot be an irreducible representation of Z. So what I basically prove from here is that if V is irreducible, if and only if V is one-dimensional. And if V is one-dimensional, then it is clearly, by definition, it is a monomial representation, so result is true for these. Right? So if G is, and similar argument will work for any finitely generated abelian group. So the next step is about so let me go to the next step. So the next step is, let's take G to be finitely generated two-step nilpotent groups. So for example, the groups to keep in mind are of this nature, okay? So let's take G to be a two-step nilpotent group. And then I'm asking the parallel question, is every irreducible representation monomial? So this question was already, has already been answered by Arnall and Parshin. So this appeared in 2012. Yeah, and this is, I would say this is the paper that we happen to read together. So there they characterize, so they actually, so so what they mention is that this is not true. That means not every irreducible representation is monomial for these groups. So the next question is then, what is the characterization? How do I characterize those that are monomial? And they actually answer this question. For that, we give you one definition. It's called finite weight representations. A representation V of a group. So here, when I'm talking about groups, I always mean infinite. A representation V of a group G is said to have this finite weight with respect to, so it's finite weight with respect to the tuple H chi. If look at this space of vectors such that, okay, I want to give also name of this representation, it's phi HV. Is non-trivial and finite dimensional. So representation is called finite weight if I can find any such tuple H chi. So it's let me just say it once more. So representation is said to have finite weight with respect to this tuple H chi if this space is non-trivial and it's finite dimensional, right? I mean, I want non-trivial also. This really means that when I'm looking at its restriction, chi should appear. There is a chi vector, right? Eigenvector here, and so that's the non-triviality part, and the condition is finite weight. I say representation has finite weight if I can find such H chi. So the theorem that Arnold and Parshin proved was that let G be a two-step finitely generated nilpotent group, or finitely nilpotent group, then an irreducible representation V of G is monomial if and only if it has finite weight. Okay, so one would wonder that how did this finite weight condition come into the picture? Okay, so the finite weight condition actually, so no, I mean it's called finite weight if I can find any H chi such that it has finite weight with respect to H chi. So okay, let me just say this. Finite weight with respect to H chi. And a representation V is called finite weight if there exists H chi such that V has finite weight with respect to H chi. So that just says that there is one H and chi such that this condition is satisfied. There is no condition on H. You mean the dimension, or it's the dimension is finite. Finite dimensional. I mean, I'm not saying dimension, what should be the dimension? No, there's no word. I mean, finite weight is just a definition. I mean, it's not that I'm saying finite weight of this, I mean, finite weight 5, that means that, no, I'm not. Finite weight is just a definition for this having such finite dimensionality as the condition being satisfied, okay? So, yeah, it's not my definition, I'm sorry. So I should say that the definition of finite weight was already in the literature. So let me just take you to some other related questions where actually at least one place where finite weight already had appeared. So for that, we'll have to look at the parallel question for the case for nilpotent Lie groups. Okay, so one can basically start, I mean, these questions of course came into the nature because one can start, so here is another, I would say just, the motivation also came from these, okay. So suppose G is a nilpotent Lie group, then, and here, when I'm looking at V, so to begin with, we look at unitary irreducible representation. I look at the unitary irreducible representations. Okay, that means that I have a continuous map from G to the unitary operators of a Hilbert space, and then I can ask whether V is monomial. So this already appeared in the literature. So the proof that I have seen was in Kirillov's work, where he gives, okay, maybe I should be a little more precise here. J is simply connected. Okay, so for G simply connected nilpotent Lie groups, Kirillov said that Kirillov answered by using the orbit method, and he was trying to study all the representations. So this was not the main goal. It came out as an outcome, is that every unitary irreducible representation of G is monomial. Okay, and and the next, so now there's work by I.T. Brown in 1973. So where instead of looking at this nilpotent Lie groups, he started studying the kind of groups that I'm interested in. Those that is, G is finitely generated discrete nilpotent Lie groups, but still continuing to study unitary representations. Okay, so V is still unitary, and then he started asking, for these groups, is every unitary irreducible representation monomial? And he gave a counterexample for a unitary case that this is not true, and he proved the result. That let G be a finitely generated discrete nilpotent group, then a unitary irreducible representation of G is monomial if and only if it has finite weight. So he was the one who gave this condition, finite weight, and he actually gave a counter example for this unitary representations with the, he actually constructed a counter example for these groups. He gave a unitary irreducible representation which was not monomial for these groups. He was looking at these, but here was assuming the unitary condition. And so I want to say that the work of Parshin was motivated by Brown's work, and once they started looking at not the unitary but algebraic representation, they found that the same representation turns out to be giving the characterization of monomial representation. So this led Parshin to conjecture that this is going to be true in the more general setting of any nilpotent group. So they did here, they proved it only for two-step nilpotent groups. So Parshin conjectured that it's true for all nilpotent groups, finitely generated discrete nilpotent groups. Okay, so whether this, so let me call this Brown's characterization. Okay, so so this conjecture has been recently proved by Belush and Gorczynski. Okay. So rather I should say that we had some proof, but when we sent it to Arnal, he pointed out a gap to us. And that's how we figured out there was something that we were missing there, and they fixed that, and that's how otherwise the ideas were both modeled on Brown's ideas. We were trying to push Brown's proof to the discrete setting, how much can one do. Okay, so let me give you idea how does it work for the nilpotent groups, and then I'll tell you how the super solvable setting works. Okay? Now, before giving the proof, let's go back to finite group setting. Let's try to recall why is every finite nilpotent group monomial, and then we'll see what exactly doesn't work for the infinite setting, right? So let's say G is a finite nilpotent, and V an irreducible representation of G. Now, because G is a nilpotent group, there exists a subgroup A of G such that A is abelian, non-central, normal subgroup of G. Right? This just follows because G is nilpotent, so I can look at the lower central series and get this subgroup A. Now, once I have this subgroup A, let chi be irreducible. So here it's by irreducible, I mean irreducible representations, inequivalent irreducible representation. A is abelian, so it's just a character such that when I restrict V to A, chi is a constituent of it. Maybe I should have made a remark. I can assume V is faithful always, right? Because if it's not faithful, then I can come to a smaller group. One can do by induction. So yeah, maybe I should have said here, I'm giving the proof by induction. Okay, so for the abelian groups, everything is okay, and okay, should say induction on the cardinality. If the group is trivial group, then everything is clear. And if otherwise, I can assume that my representation is faithful because I'll come to a smaller group and then by induction it will be true. So I'm also assuming that V is faithful. Yes. It's important for the full argument that I'm giving here, but yes. Now, let's say chi is an irreducible representation of A such that this is true. Let me use the same notation. So let's consider VA, okay, such that V is in V. Chi A chi AB. Okay, for all A. Sorry, I'm back here. So I'm denoting the representation by pi. So I'm again looking at, these are exactly the vectors that I've looked at there. VH chi, here I'm just looking at VA chi. Okay, and let's say S is the stabilizer of chi in G. So chi is a character of a normal subgroup, so I can talk about it's a stabilizer, and let's say S is the stabilizer. Then from the condition that I have for the A being a abelian non-central normal subgroup and V is faithful, says that stabilizer is strictly less than G. It's a strictly subgroup, it cannot be equal to G, okay? And V is isomorphic to induced representation from S to G of this VA chi. So this S acts on VA chi, so it becomes a VS representation, and we can show that V is isomorphic to this induced representation from the stabilizer to G. Stabilizer is not equal to G here, notice that. Now I can just use induction because S has cardinality strictly less than the cardinality of G. This is a finite dimensional representation of S, and I can just use induction here. And therefore, induction is transitive, so V is monomial representation. So this is the proof that we all do for the finite nilpotent groups. So let's see if I want to do it for the infinite nilpotent group, what are the difficulties, right? So here I didn't assume anything like a finite weight representation. The reason is that here I was always given this chi, right? So this existence of this A is there even if I'm working with infinite groups. But there I cannot talk about this chi. It's exactly the problem that I said for Z. If I have an infinite dimensional representation, and then I cannot guarantee existence of this one-dimensional character. So now, as I'm saying, I'm talking about, let's say G is infinite group. So here let's just say two cases, V is finite dimensional and V is infinite dimensional. So if V is finite dimensional, almost the same argument works. Just that same argument would work for the finite dimensional case. And of course, we can check that finite dimensionality always is there. I mean, it's given to me whenever V is finite dimensional, it always has finite weight. I can always work with this A and this chi. There will be A and the chi here, right? So the question is for infinite dimensional representation. So this question that I'm talking about this argument doesn't work for the infinite dimensional representations of G. Right? So now onwards, I assume V is infinite dimensional. Okay, so V is infinite dimensional. Now, so I cannot use this, and so that's having. Now let's see what are the problems that I'm going to face for the infinite setting. Now I want to prove that V is isomorphic to induced Hg chi for some H chi. So let's also assume that V has finite weight with respect to H naught chi naught. This H chi may not be equal to this H naught chi naught, and usually this is not the case. I mean, for this has to satisfy very special properties. So let's say I'm given a tuple H naught chi naught and V has finite weight with respect to this. I want to prove that V is isomorphic to this for some H chi, right? Okay. Now, now if I want to prove these two are isomorphic, as I cannot use these kind of arguments, and and H naught may not be a normal subgroup. I'm not given that H naught is a normal subgroup, right? So I need to find out how do I start with this problem. I cannot talk about stabilizer of chi and all. So that's where the first problem starts. So then the first question that one asks is, if I want to prove this is isomorphic, that means this representation has to be irreducible, right? V is irreducible. So I need to ask, when is this induced representation irreducible, right? So, and here, so if G is finite, I know that a representation is irreducible if and only if, so G finite says that in that case, this is irreducible if and only if this is true. So I'm looking at only complex representation. If I know that intertwiner is 1, then I know representation is irreducible, and this is if and only if. This does not turn out to be the case for infinite groups. So what is true is, now let me define something sure irreducible. Okay, so representation V of G is called sure irreducible. Endomorphism, when I look at the endomorphism algebra, it's isomorphic to C. Okay, that I call as, and for the infinite groups, it turns out that this is a weaker condition. Sure irreducible does not imply irreducible. So then one has to worry about whether, so there are two questions, whether my representation is sure irreducible, and then is it irreducible? I mean, we did not know how to start doing, proving something is irreducible, right? So the questions that we worry about, when is this sure irreducible? Okay, and does sure irreducible imply irreducible? The answer of this, we don't still know in general, but for the nilpotent groups and supersolvable groups, we know that this is true. That whenever representation is sure irreducible, and it is of the nature induced from a one-dimensional character from a subgroup to G, then it is irreducible. I'll state this result. So let me just state for this result. Finitely generated, discrete, discrete. Here, I mean, their work is for nilpotent, and you can also do for super solvable as well, it works. Discrete super solvable group. Then, is sure irreducible. Then this is sure irreducible implies. Okay. So here also I want to say that the proof that we have works only in these kind of representations. The representations that are induced from one-dimensional character of a subgroup. That's a very special case that we could do that. And so we don't know the answer for this in general. That there are examples, but not for there's no example that we have for the nilpotent groups, for sure irreducible, which is not irreducible. Don't know. And for the first question is concerned, when is this induced representation sure irreducible? So for that, there is a theorem that we found by Putzko, where he was looking at, for some reason, non-unitary representations. It's a very short paper, and there he proves this result. It's isomorphic to it's analogous to what we have in the finite case. So this is exactly the result that we have for the finite case, right? That the endomorphisms algebra of this is isomorphic to as vector spaces. And therefore, if I want to know that whether this representation is sure irreducible, that means the tuple h chi should satisfy the condition that chi g is not equal to chi on h intersection hg. That's the condition, final condition I'm looking for. Right? Can I find, I start with h naught chi naught, can I come to the tuple h chi such that this condition is satisfied? Right? So that then induced representation will be sure irreducible. And this actually turns out to be the case. And here one uses so if I'm starting with h naught and chi naught. If h naught chi naught already satisfy this condition, then okay. Then I'm still not done. If maybe I should say this. Yes. So if h naught chi naught satisfy, let's say this is star, then what we prove is that there exists an intertwiner between a non-trivial intertwiner between the irreducible representation B and this induced representation. And now, by that theorem, this is irreducible, therefore these are isomorphic. That's exactly what we use, okay? And so eventually the question really boils down to, can I prove this? Can I find such an h chi? And that exactly, that works through, so for this, we really need to look at the finer aspects of group here. So here, we start asking, okay, what if such a G exists? What can I say about such a G? So suppose h naught chi naught does not satisfy this condition, then what is this G? We actually prove that such G should belong to the normalizer of the radical of h naught. So here, radical of h naught is nothing but G is in G such that G to the some power. Okay, and then in between, we also have this root h naught, and here I want to make a comment that if G is nilpotent, root h naught is a group. But if G is not nilpotent, or for example in supersolvable case, this need not to be a group. Okay? In that case, so this, what I'm saying here works for the nilpotent, but for the supersolvable, one has to worry a little more. It doesn't work through just this way. So one has to worry a little more. So here, let's say, I'm only talking about mostly about G nilpotent. And now I have h naught. And so then, the next property that we also use is that root h naught is a finite index subgroup of root h naught. Okay? So after that, it's basically, trying to find nicer ways so that I can go up firstly in Hertz length. So I use induction on the Hertz length of the group G and on the group G and group h naught. Then we go up in the Hertz length, and then eventually we come to a point where we have to only solve a finite index problem. And then we again try to find ways of going up till we match this condition. And then we show that there exists h chi. So we modify our h as we go along and our character chi till we end up getting such a tuple h chi such that this condition star is satisfied. Okay, so that's basically what works for the nilpotent groups. Okay, so yeah, I have only 8 seconds. Yeah, I think I'll stop here. So I have mentioned the differences with super solvable case.
And such a beautiful talk. Thank you very much. Are there any questions and or comments?
This one, oh, this was a conjecture. This was a conjecture. Yes. So I should say, I mean, I don't want to take a credit of this. This was actually done by, I mean, finally finished by Belishpaka and Gorchinsky. That result, it's okay. I should say, this is exactly what we missed. We ended up doing that, but we didn't realize this problem is there for the nilpotent groups. I mean, discrete nilpotent groups may have this, or discrete groups may have this problem. But irreducible may not be equivalent to sure irreducible. So what we did was only up to sure irreducible. So they proved this result for the nilpotent case. And so I want to say that they proved this conjecture. So we kind of proved sure irreducible. Yes, because of the finite weight condition. Yes. Yes. Usually we go up. It may not be like, sometimes we may have to go a little bit, like we find something else there. But yeah, usually it's up. Like in Hertz length as well. If chi is the, wait a minute. So if chi is the trivial representation, then H is a normal subgroup, right? Oh, no, wait, sorry. What I'm saying. So if, okay, I have thought about it. I'll tell you. I'm not able to think just right now. I'll tell you. Yeah, I've thought about it, but I'm not.
Any other questions or comments?
Yes, so we don't know in general whether sure, so okay, I should say irreducible implies sure irreducible. Here it's finitely generated, I'm looking at that, where it's important. But we don't know when is sure irreducible implies irreducible. This is a very special case, special kind of representations we are looking at. And when I know this is sure irreducible, we are able to say this is irreducible. But we don't know in general. Yes. It's a yes. So they have, there is an example, not for the nilpotent case, but for SL2Z. There is an example of a representation which is sure irreducible, but not irreducible. Yes. I should say not really very, no, it's not a very difficult result. So actually, if H is normal, if one assumes H is normal, it's like usual arguments that work. And then for the nilpotent case, H is subnormal, and then one uses kind of induction. For the super solvable, one has to worry a little more because not every subgroup is subnormal. And then we define what's called some almost normal groups. They satisfy some condition, under those conditions we prove it. And I'm not saying it's a very difficult thing, but I would say that I didn't notice it earlier when we were doing this. So it came out only later. Yes, please.
Yes?
Okay, yes, in the proof, I use some sort of, there are, for example, if I want to look at index n subgroups, I mean, those kind of arguments I use finitely generated. So there are things where in the proof where I use finitely generated. We only, yeah, exactly.
Any other questions or comments? Well, then please join me in thanking our speaker again.